Let's talk about the invisible rules that keep our buildings from falling down. Seriously, there are entire books of them. And in India, one of the most important rulebooks of all, IS 456, is getting a massive update. This new draft could completely change how the country builds its future. So let's dive in and see what's inside.
I mean, really think about it for a second. When you're looking up at a giant skyscraper or walking through a huge shopping mall, what is actually holding all of that up? What's fighting against gravity, against the wind, and even against earthquakes?
Well, it turns out it's a really dense, incredibly detailed set of rules, a building code. And right now, the most fundamental code for every single concrete structure in India is going through a huge evolution. And by looking at what's changing, we're getting a sneak peek into the future of engineering.
So what we're looking at here is the draft for IS 456. You can think of it as the master blueprint for anything built with concrete. And these documents, they're not set in stone. They have to evolve, right? They've got to keep up with new materials, new tech, and just a better understanding of how buildings behave in the real world.
Okay, so the first huge shift we see in this draft is basically a demand for honesty. It's pushing engineers to create computer models that are way more realistic, way more truthful about what a building is actually like long before anyone starts pouring concrete.
And this gets to a really cool concept called effective section properties. See, in the past, a lot of models just kind of assumed materials were perfect, like a solid, flawless block. But we all know that's not how things work. Concrete, by its very nature, has tiny, unavoidable microcracks. This new rule forces the computer models to see those cracks, to account for them, giving a much more accurate picture of a building's real strength.
And yeah, this slide just nails the difference. We are literally moving from an idealized, perfect world to one that accepts reality. The draft says you have to consider these cracked properties not just for the ultimate worst-case scenario strength, but for the building's day-to-day performance, what engineers call serviceability. It's about designing for the real world, not some perfect simulation.
Okay, that makes sense for the building itself. But a building is only as strong as its foundation, right? So if the model of the structure is getting more realistic, what about the ground it's sitting on?
You guessed it, the new draft wants a much smarter approach here, too. It's making engineers model what's called soil-structure interaction. Basically, you can't just pretend the ground is a solid block of granite anymore. You have to model it more like a really firm mattress. It has some give, it has flexibility depending on the soil, and that flexibility has a direct impact on the entire building sitting on top of it.
So, building on that idea of a more realistic model, the next big update introduces a way more rigorous method for checking a building's stability against any sideways forces, like strong winds or an earthquake.
And the core of this whole thing is a new metric called the Stability Index, or just Q. Think of it as a report card for every single floor of the building. It gives a score based on how slender or wobbly that story is, and how vulnerable it is to something called the P-delta effect, which is basically a domino effect where a building that's leaning just a little bit creates extra forces that can make it lean even more.
Now this is where it gets really clever. The Q score you get isn't just a number for a report. It's an instruction manual. It tells you exactly what kind of analysis you have to run. If the score is super low, a standard pretty simple analysis is fine. But as that score climbs, meaning the building is more slender and at risk, the code says, nope, you've got to bring out the big guns, and it demands a way more complex and rigorous analysis.
So the takeaway here is huge. It's not a one-size-fits-all approach anymore. The building's own design, its very shape, now dictates the level of testing it has to go through. The structure itself is telling the engineer how to prove it's safe.
All right, now we're getting into some of the most dramatic new requirements. The new draft is pushing engineers to design not just for everyday life, but to actually plan for extreme, you never think it'll happen kinds of events.
It's called progressive collapse analysis, and it is a massive job. For important buildings, engineers have to go into their computer model and, one by one, digitally remove every single important column or beam. And each time they remove one, they have to rerun the analysis to see if the rest of the building can handle the new load and stay standing. It's literally like playing a high-stakes game of Jenga with a skyscraper on a supercomputer just to make sure losing one piece doesn't bring the whole thing crashing down.
And this quote from the draft itself really says it all. The goal here isn't just about preventing one little part from failing, it's about making sure the entire structure doesn't collapse. This is a huge shift toward building resilience from the very beginning.
And it doesn't even stop there. The draft also brings in new requirements for blast analysis, another one of those unthinkable scenarios. It forces engineers to simulate how a building would hold up against a massive, instantaneous force, again, using those super advanced computer models.
Okay, so we've covered these really complex models and extreme scenarios, but how does all this high-level theory actually translate into a safer building in the real world? Let's zoom in on a couple of small but crucial details.
Let's start with this number, 64 millimeters. Seems pretty random, right? Well, according to this new draft, that's the required thickness of concrete that has to cover a 32 millimeter steel reinforcing bar.
You might be wondering, why on earth should I care about a few extra millimeters of concrete in a massive building? What possible difference could that make?
Well, it turns out it makes all the difference in the world. That layer of concrete is like armor for the steel skeleton inside the building. It's the first line of defense against rust and corrosion, and maybe most importantly, it acts as a fire shield, insulating the steel so it doesn't get too hot and lose its strength. That tiny detail is absolutely fundamental to a building's safety and how long it's going to last.
And that's just one example. This new draft is raising the safety bar everywhere you look. It's proposing stricter limits, like saying certain foundations can't have any uplift at all. It's also increasing the minimum size for columns in most buildings. Every one of these changes is part of a bigger push toward buildings that are just fundamentally tougher and more resilient.
So, when you put it all together, from computer models that are smart enough to see tiny invisible cracks, to stability checks that are custom fit to a building's unique shape, to designs that literally plan for chaos, you realize this isn't just an update to a document, it's a whole new philosophy for building a safer world.
And it really makes you wonder, are we just looking at the next set of rules for the cities we'll build tomorrow? Or is this something bigger? Is this the beginning of a completely new, smarter, and more resilient era in how we design the world around us?